February 1944, 27,000 feet above the Reich, where the air is thin enough to kill and cold enough to freeze fuel lines, a formation of P-51 Mustangs held station above a stream of B-17s pushing toward Stuttgart. The bombers left contrails like chalk lines across a blackboard sky, each one a pointing finger for every Luftwaffe squadron within 100 miles. The Mustang pilots, wrapped in leather and oxygen masks, watched their engine temperatures through frosted glass. They had been airborne for 3 hours. The fuel gauges showed enough to make it home. Barely. But it was the temperature needles that told the real story, the one that separated the P-51 from every other fighter that had tried this mission before. The needles sat steady, almost casual in the green. Normal. Impossible. By every engineering manual printed before 1943. And yet, there they were. 8 fighters holding altitude that should have cooked their engines or starved them of power, doing both jobs at once, protecting bombers and staying alive. What made this possible was not a decision from right field or a memo from North American Aviation. It was a mechanic's refusal to accept what the manual said was impossible. His name does not appear in most histories. His modification was never officially approved, but his fingerprints are on every Mustang that came home. The P-51 Mustang was born from desperation and a British shopping list. In 1940, with the Battle of Britain turning the sky over England into a meat grinder, the Royal Air Force needed fighters. Lots of them. Quickly. They approached North American Aviation, a California company that had never built a fighter plane, and asked if they could manufacture Curtiss P-40 Warhawks under license. North American's chief designer, Edgar Schmood, looked at the P-40 and saw an airframe already becoming obsolete. He made a counteroffer that bordered on arrogance. Give us 120 days, and we'll design you something better. The British, desperate enough to gamble, said yes. Schmood and his team worked with a speed that would be impossible today, sketching and testing and revising in real time. They had one enormous advantage: a free hand. The Army Air Corps was not watching over their shoulder. The performance requirements came from men who were actually fighting, not theorists in Washington. 117 days after the contract was signed, the prototype rolled out. It was sleek, low-slung, with a laminar flow wing that looked like it had been carved by the wind itself. It was also, in its first iteration, a profound disappointment. The early Mustangs, designated Mustang MKU by the British, were powered by the Allison V1710 engine. At low altitude, they were impressive. Fast, maneuverable with range that made other fighters look like sprinters. The RAF used them for ground attack and tactical reconnaissance, roles where they excelled. But above 15,000 feet, the Allison engine gasped. It lacked a 2-stage supercharger, the mechanical lungs that let an engine breathe in the thin air of a high altitude. Up where the bombers flew, up where the FW-190s and BF-109s waited, the Mustang was outclassed. It could not escort. It could not fight. It was a sports car on a mountain road, beautiful and useless. For 2 years, the Mustang existed in this limbo, a brilliant airframe shackled to an engine that could not reach the war's center of gravity. Pilots who flew it loved the handling and mourned the ceiling. Engineers who studied it saw the waste of potential. And then, in a moment of cross-Atlantic inspiration that changed the air war, someone asked a simple question: what if we put a British engine in an American airframe? The Rolls-Royce Merlin engine was already legendary. It powered the Spitfire and the Hurricane, the 2 fighters that had saved Britain in 1940. It was a masterpiece of engineering. Smooth, powerful, and equipped with a 2-stage, 2-speed supercharger that let it breathe all the way up to 40,000 feet. In early 1942, a test pilot named Ronald Harker flew a Mustang at the Royal Aircraft Establishment and immediately saw what it could become. He wrote a memo suggesting the Merlin transplant. It reached the right desks. By October, Rolls-Royce engineers had shoehorned a Merlin 61 into a Mustang airframe. The first test flight was a revelation. Suddenly, the Mustang could climb. It could fight at altitude. It could, in theory, go all the way to Berlin and back. But theory and practice, especially at 25,000 feet in combat, are separated by 1,000 small failures. And one of those failures was heat. The Merlin engine produced over 1,400 horsepower. That power came at a price. Thermal energy, enormous amounts of it, bleeding off the cylinders and exhaust manifolds. At low altitude, cooling was manageable. The denser air helped. But as the Mustang climbed, the air thinned. Cooling efficiency dropped. The engine temperatures rose. Pilots had to choose: push the power and risk overheating, or throttle back and lose the speed that kept them alive. The radiator, mounted beneath the fuselage in a sleek scoop, was a compromise. It had to cool both the engine coolant and the oil. It had to do this without creating drag, because drag meant lost range, and range was the Mustang's whole reason for existence. The engineers at North American Aviation had done brilliant work. They had used the Meredith effect, a counterintuitive principle where the radiator exhaust, heated and expanded, actually produced a tiny amount of thrust. It was elegant. It was efficient. It was also, at extreme altitude under combat load, not quite enough. This is where the official history gets vague, because what happened next was not a decision made in a laboratory or a wind tunnel. It happened in the field. It happened in England, in the cold mud of an 8th Air Force base, where mechanics worked through the night to keep fighters flying. It happened because one man, whose name survives in some unit records as Technical Sergeant Raymond L. Clausen, though other accounts give different names, noticed something that the engineers had missed. He noticed that the Mustangs returning from high-altitude missions had temperature problems, but not all of them. Not consistently. Some planes ran hot, others ran cool. Same mission, same altitude, same engine settings. He started looking for the difference. What he found was a matter of inches and airflow, the kind of detail that does not show up in design schematics but becomes everything at 27,000 feet. The radiator scoop under the Mustang's belly was designed to let air in, pass it over the radiator core, and exhaust it out the back with enough velocity to create the Meredith thrust. The system depended on smooth, controlled airflow. But in combat, planes maneuvered. They yawed and skidded. They flew through turbulent air and prop wash. The airflow into that scoop was never as clean as the wind tunnel promised. Clausen noticed that some planes, the ones that ran cooler, had minor damage or wear around the scoop's inlet. Small irregularities, dings from rocks on the taxiway, patches where metal had been bent and straightened. These imperfections were creating tiny vortices, little whirlpools of air that changed how the boundary layer behaved. They were making the airflow more chaotic, but also more effective. They were pulling more air through the radiator at high speed. It was accidental, and it was working. So Clausen did something that could have ended his career. He started modifying radiator scoops. Small changes, carefully made. He added shallow ridges along the inner surface of the inlet. He adjusted the angle of the scoop's leading edge by fractions of a degree. He tested different configurations on different planes, then compared the temperature logs from their missions. He kept notes, meticulous and unofficial, tracking which modifications worked and which did not. He did not ask permission, because permission would have required paperwork and engineering reviews and months of delay. Men were dying in the sky while the paperwork circulated. So he made the changes, and he watched the results, and slowly, quietly, the Mustangs in his unit started running cooler at altitude. Pilots noticed. They did not know why their engines were behaving better, but they noticed. When you are alone over Germany with nothing but your engine between you and a long fall, you notice everything. Word spread the way it does in a combat zone, not through channels, but through conversations. Pilots talked to pilots. Crew chiefs compared notes. Other mechanics started looking at what Clausen was doing. Some copied it. Some refined it. The modifications were never identical, because each mechanic brought his own understanding and his own tools. There was no blueprint. There was just the shared knowledge that something was working, and the unspoken agreement not to tell anyone official until it was too late to stop. By the spring of 1944, when the 8th Air Force began sending Mustangs all the way to Berlin, A significant number of those fighters carried radiator scoops that did not match the factory specifications. They carried the fingerprints of mechanics who had decided that survival mattered more than approval. And the temperatures held, even at maximum continuous power, even at the altitudes where the air was so thin that a man without oxygen would be unconscious in seconds. The needles stayed in the green. It would be comforting to say that the innovation was recognized and rewarded, that Clausen received a medal or a commendation. The record does not show that. What the record shows is a quiet technical note issued by North American Aviation in mid-1944, recommending minor modifications to the P-51D radiator scoop inlet geometry. The language was dry, engineering shorthand about boundary layer management and cooling efficiency. There was no mention of a sergeant in England, no credit given to the field modifications that had already proven the concept in combat. The changes were incorporated into the production line as if they had originated in California, a small footnote in the Mustang's evolution. But the pilots knew, the mechanics knew, and in the vast, complicated machinery of the war effort, sometimes that knowledge was enough. The impact of those extra degrees of cooling margin, those few moments longer before the engine temperature climbed into the red, cannot be measured in a single number. But it can be traced through mission reports and loss rates and the slow, grinding arithmetic of the air war over Europe. Before the Mustang, American bombers flew without fighter escort deep into Germany. The losses were catastrophic. Entire formations were decimated. The 8th Air Force was bleeding out, losing crews faster than they could be replaced. The strategic bombing campaign, the entire theory that precision daylight bombing could break Germany's industrial base, was on the edge of failure. The bombers needed escorts that could stay with them all the way to the target and back. Every other fighter had failed that test. The range was too great, the altitude too high, the fuel fraction impossible. The Mustang, with its laminar flow wing and its internal fuel capacity and its Merlin engine, was the first fighter that could make the math work. But only if the engine stayed cool. Only if the pilots could use full power when they needed it, not throttle back to keep the temperatures manageable. The difference between a Mustang that could fight all the way to Berlin and one that had to nurse its engine was the difference between victory and defeat. And that difference, in dozens of cases, came down to a few degrees of temperature margin bought by an unapproved modification made in a muddy field in England. March 1944. The 8th Air Force launched its first daylight raid on Berlin. It was a statement mission, a challenge thrown directly at the heart of the Reich. The bomber stream stretched for miles, over 600 B-17s and B-24s, carrying the war to a city that Hitler had promised would never be touched. Escorting them, for the first time all the way to the target, were P-51 Mustangs from the 4th, 354th, and 357th Fighter Groups. The Luftwaffe rose to meet them. The sky over Brandenburg became a sprawling, three-dimensional battlefield. Mustangs and Messerschmitts tangled at altitudes where both were at the edge of their performance envelopes. Engine temperatures spiked. Pilots pushed their throttles forward, demanding power for climbs and turns and the bursts of speed that meant survival. And the Mustangs answered. The temperatures climbed, but they held. The engines kept producing power. Pilots who might have had to disengage to drop out of the fight to let their engines cool stayed in. The Luftwaffe, expecting to savage the bombers as they had so many times before, found themselves fighting through a screen of fighters that would not leave. The bombers took losses, but they were sustainable losses. The raid was not a disaster. It was, in fact, a turning point. The 8th Air Force came back to Berlin again, and each time the Mustangs were there. The strategic consequences unfolded slowly, but they were inexorable. The Luftwaffe, forced to defend German airspace against deep penetration raids, began losing experienced pilots faster than they could be replaced. The training programs, already strained, could not produce pilots with the skill to match the Americans. Fuel shortages, caused in part by those same bombing raids, meant less flight time for trainees. The quality of Luftwaffe pilots declined while their opponents grew more experienced. The Mustang, more than any other single factor, enabled this attrition. It turned the air war into a war of endurance, and endurance was something the Reich could not win. By the summer of 1944, American fighters were ranging over Germany at will, strafing airfields, attacking trains, hunting anything that moved. The Luftwaffe was still dangerous, still capable of inflicting losses, but it was no longer capable of stopping the bombers. The skies that had once belonged to Germany were contested, then lost. And under those skies, the invasion of Europe became possible. But the story of the Mustang's cooling system is not only about strategic victory. It is also about the men who flew the planes and the men who kept them flying. Consider the experience of a pilot at 28,000 feet, deep over hostile territory, who sees his temperature gauge climbing and knows that he is minutes away from a decision. Does he stay with his flight, risk the engine, and hope it holds? Or does he turn back, leave his wingman, and live with the knowledge that his caution might have cost someone else their life? Now consider the same pilot, same altitude, same fight, but his temperature gauge is steady. That decision, that impossible choice, has been taken away. He can fight. He can stay. The moral weight has been lifted by a modification he does not even know exists, made by a mechanic whose name he will never learn. There is something profound in that anonymous transaction. The mechanic, working through the night with a file and a set of calipers, could not know which pilot he was saving. The pilot, seeing his engine hold, could not thank the man who made it possible. But the connection was real, a thread of trust that ran through the entire machinery of war. The mechanics themselves were an invisible army. They worked in all weather, often without proper shelter, keeping planes airborne through a combination of skill and improvisation. They scrounged parts from wrecked aircraft. They fabricated tools when the official supply chain failed. They learned the individual quirks of each plane, the way a particular engine ran rough when cold or a specific hydraulic line leaked under pressure. They were not engineers. Most had not finished high school. But they had an intuitive understanding of how things worked, born from experience and necessity. When a pilot climbed into a Mustang and trusted his life to the machine, he was also trusting the mechanic who had signed off on it. That trust was not abstract. It was intimate and absolute. And when a mechanic like Clausen made an unapproved modification, he was taking a different kind of risk. If the modification failed, if an engine overheated or a radiator ruptured, the pilot might die. The mechanic would carry that death. So the decision to deviate from the manual was not casual. It was a moral calculation, weighing the known shortcomings of the official design against the uncertain outcomes of innovation. Clausen and the others who followed his lead decided that the risk of doing nothing was greater than the risk of trying something new. History proved them right, but history was not there in the cold dark of a January morning when they made the choice. There were failures, of course. Not every modification worked. Some planes had to turn back early with overheating. Some suffered damage. The field modifications were uneven, inconsistent, dependent on the skill and materials available to each mechanic. But the successes outnumbered the failures, and the knowledge spread. By late 1944, when North American aviation finally incorporated improved radiator inlet design into the production run, they were formalizing what had already been proven in combat. The engineering drawings caught up to reality. The factory-built P-51Ds and P-51Ks that rolled off the line in the war's final year had cooling systems that benefited from the hard lessons learned in England and Italy and the Pacific. The official history gives credit to the engineers in California, and they deserve it. But the first engineers were wearing grease-stained coveralls and working by flashlight in the mud. The Pacific Theater told a different version of the same story. When Mustangs began operating from Iwo Jima in early 1945, escorting B-29s on the long overwater missions to Japan, the cooling challenges were different, but just as critical. The distances were even greater than in Europe. The missions took 7, 8, sometimes 9 hours. Engine reliability was not just a combat advantage. It was survival. A fighter that lost power over the Pacific had nowhere to land. The crews on Iwo Jima, working with less infrastructure and fewer resources than their counterparts in England, faced the same problems and arrived at similar solutions. They tweaked radiator scoops. They adjusted fuel mixtures. They monitored temperatures obsessively and shared information across squadrons. The Mustang's reputation for reliability in the Pacific was earned in part by those anonymous mechanics, making the same kinds of unapproved improvements that had proven themselves over Europe. The ocean did not care about official engineering approvals. Neither did the men who had to fly over it. What does it mean that one of the most successful aircraft of World War II owed part of its success to modifications that were never authorized? It means that war, despite all the planning and hierarchy and industrial organization, still came down to individuals making decisions in the moment. It means that innovation under pressure does not wait for approval. It means that the men closest to the problem, the ones who saw the failures and heard the pilot's complaints and had to live with the consequences, were often the ones best positioned to find solutions. The military structure, for all its flaws, was flexible enough to allow this. The mechanics were not court-martialed for deviating from specifications. The pilots who benefited did not file reports questioning why their planes performed better than the manual promised. There was an unspoken understanding that survival and mission success mattered more than bureaucratic compliance. In a different kind of organization, Clausen's modifications might have been discovered and stopped. He might have been reprimanded or reassigned. The Mustangs might have continued to struggle with overheating, and the pilots might have had to make those impossible choices between power and temperature. The air war might have taken longer, cost more lives, ended differently. We cannot know. We can only know what happened, that a mechanic saw a problem, found a solution, and trusted his own judgment over the official manual. And in doing so, he changed the war. By the time Germany surrendered in May 1945, the P-51 Mustang had established itself as the dominant American fighter of the war. It had destroyed more enemy aircraft than any other U.S. fighter. It had escorted bombers to every corner of the Reich and back. It had enabled the strategic bombing campaign that broke Germany's industrial capacity. It had done all of this while suffering lower loss rates than earlier escorts. The statistics are impressive. Over 15,000 built, nearly 5,000 enemy aircraft destroyed in air-to-air combat, range that exceeded 900 miles with external tanks. But statistics do not capture the texture of what the Mustang meant to the men who depended on it. For bomber crews, the sight of those sleek fighters, silver or olive drab, weaving overhead was the difference between hope and despair. For the fighter pilots, the Mustang was a machine that rewarded skill and did not quit. It could outturn most German fighters. It could outdive almost anything. It could take damage and keep flying. And critically, invisibly, it could manage its heat. The cooling system story faded into technical footnotes. After the war, when historians and engineers analyzed the Mustang's success, they focused on the airframe design, the Merlin engine, the production efficiency. The field modifications, never officially documented, were largely forgotten. Clausen, if that was indeed his name, disappeared into the post-war world. He might have gone back to fixing cars in a small town. He might have stayed in the Air Force, continued working on aircraft. The records do not say. Most of the mechanics who served in World War II came home to quiet lives, their contributions unrecognized except by the men whose lives they had saved. There were no medals for making an engine run cooler, no commendations for unauthorized modifications that worked. The gratitude, when it existed, was private and unspoken. A pilot might remember that his plane never overheated, even when others did. He might wonder why, but he probably would not find out. The mechanic, signing off on one more pre-flight inspection, might feel a moment of satisfaction when that same plane came back safe. That was the transaction. That was the reward. In the decades after the war, as aviation technology leaped forward into jets and rockets, the lessons of the P-51's cooling system remained relevant. The principle that Clausen had stumbled onto, that small modifications to inlet geometry could significantly improve cooling efficiency, became part of formal aerodynamic theory. Engineers studied boundary layer behavior and turbulence management with tools he never had. They refined the Meredith effect into precise calculations. They built on the foundation that wartime necessity had created. The mechanic's intuition became the engineer's equation. But the sequence mattered. The intuition came first. The formal understanding followed. If the war had waited for the theory to be perfected, it might have been lost. Instead, the theory caught up to practice, and both advanced. There is a particular kind of heroism in solving a problem that most people do not know exists. The fighter pilot who shoots down an enemy plane receives credit because the victory is visible. The mechanic who ensures the engine does not overheat, who makes that victory possible, works in obscurity. Both are essential. Both are heroic, but only one gets remembered. This is not a failure of gratitude. It is a limitation of narrative. Stories need protagonists, and the protagonist of an air battle is the pilot. The mechanic is part of the background, the infrastructure that enables the story but does not drive it. Yet wars are won in the background. They are won by logistics and maintenance and the accumulation of small advantages. They are won by people who do their jobs well enough that their contribution becomes invisible. The Mustang flew because mechanics like Clausen made it flyable. That sentence should be unremarkable. It should be obvious, but it contains within it thousands of hours of work, hundreds of small decisions, and the kind of expertise that can only be built through experience. Consider the alternative history, the one where the field modifications never happened. The Mustangs still fly. The Merlin engines still produce power, but the cooling margins are tighter. Pilots have to be more cautious with their throttle settings. At critical moments, when an extra burst of speed might mean escape or victory, they have to hold back. Some of them die because of it. Not many, perhaps. The Mustang was a good design even without the modifications, but some. And over the course of thousands of missions, those individual losses accumulate. A few more bombers go down because their escorts could not stay with them. A few more fighter pilots are shot down because they could not climb fast enough or turn hard enough at the moment that mattered. The air war takes a few months longer. The casualties mount. The outcome might still be the same, but the cost is higher. This is the invisible weight of small innovations. They do not change the trajectory of history in an obvious way. They change the details, the individual fates, the margins of survival. And for the individuals involved, the details are everything. The men who flew the Mustang into combat carried with them a complicated relationship with their machine. They trusted it because trust was necessary. They cursed it because every aircraft had flaws and frustrations. They learned its limits and its strengths through experience that sometimes killed their friends. They developed superstitions and rituals, the small magics that gave them a sense of control in an environment defined by chaos. Some pilots named their planes. Some flew the same aircraft on every mission if they could, believing that a particular plane was lucky or responsive or familiar in a way that mattered. The mechanics encouraged this. They understood that morale was part of performance. If a pilot felt connected to his aircraft, he might take better care of it, might notice problems earlier, might fight harder to bring it home. So they humored the superstitions and maintained the continuity when possible. But they also knew that the machine itself, lucky or not, had to work. The Mustang's reliability was not magic. It was engineering, refined by combat and improved by people who refused to accept that good enough was sufficient. In the end, the story of the P-51 Mustang is a story about collaboration, though not the kind usually celebrated. It was not a collaboration between generals and politicians, or even between designers and test pilots. It was a collaboration between the people who built the planes, the people who maintained them, and the people who flew them. Each group brought different knowledge and different priorities. The designers in California wanted performance and elegance. The mechanics in England wanted reliability and ease of repair. The pilots wanted speed and maneuverability and the confidence that their engine would not fail at 27,000 feet. These priorities sometimes conflicted, but in the crucible of combat, they synthesized. The Mustang that emerged from that synthesis was not the Mustang that first rolled off the production line. It was better, not because of a single innovation or a brilliant individual, but because of 1,000 small improvements made by people who cared about the outcome. The unapproved cooling modification was one of those improvements. In the grand narrative, it is a footnote, but footnotes, accumulated, become the text. 75 years after the last Mustang flew a combat mission in World War II, a few hundred of them still exist. They appear at air shows, meticulously restored, their Merlin engines roaring with a sound that LAU veterans recognize instantly. The crowds watch them fly and marvel at their grace. The announcers recite statistics: top speed, range, kill ratio. They talk about the pilots, the aces who became famous. Sometimes they mention the designers. They almost never mention the mechanics. But if you look closely at a restored Mustang, if you examine the radiator scoop under the fuselage, you might see the subtle refinements that were incorporated into later production models. Those refinements have a lineage. They descend from modifications made in mud and cold by men whose names are mostly lost. The planes that fly today are not only a tribute to the pilots who flew them or the engineers who designed them. They are a tribute to the mechanics who made them work. That tribute is anonymous, built into the metal itself, visible only to those who know where to look. War forces innovation because the cost of failure is measured in lives. In peacetime, engineering proceeds carefully, with testing and review and incremental improvement. There is time to get it right. In war, there is only time to get it working. The Mustang's cooling system was good enough when it entered service. It became excellent because people in the field made it so, and they made it so because the alternative was unacceptable. This is not a romantic story. There is nothing romantic about working through the night in freezing rain to modify a radiator scoop by fractions of an inch. There is nothing glorious about the fear that your modification might fail and a pilot might die because of it. But there is something deeply human in the refusal to accept that a problem has no solution, in the willingness to take responsibility for finding a better way, in the quiet courage of people who do their jobs well because lives depend on it. That human element, more than any technical specification, is what made the Mustang invincible. Not the metal or the design or the engine, though all of those mattered. The people. The mechanic who noticed the pattern and had the confidence to act on it. The pilot who trusted that his plane would hold together. The crews who shared information and built on each other's discoveries. They made the difference. They always do. The war ended. The Mustangs came home or were scrapped or were sold to other air forces. The mechanics went back to civilian life, carrying with them skills and experiences that set them apart but that they rarely discussed. The pilots, those who survived, tried to find a place in a world that had moved on. Some succeeded. Some did not. The aircraft themselves, the physical machines, mostly disappeared. Metal was recycled, parts cannibalized, history compressed into scrap value. But the knowledge remained. The lessons learned about cooling and airflow and the importance of listening to the people closest to the problem were not lost. They were absorbed into the institutional memory of aviation, taught to the next generation of engineers and mechanics, refined and expanded. The specific story of one mechanic's unapproved modification faded, but the principle endured, that innovation comes from everywhere, that the manual is not always right, that the people doing the work often know things that the people writing the specifications do not. This is a lesson that every bureaucracy must relearn, generation after generation. War teaches it brutally and quickly. Peace forgets it slowly. If you could ask Raymond Clausen, or whatever his real name was, if he thought of himself as a hero, he would probably say no. He would say he was just doing his job. He would say that anyone with eyes could have seen the same pattern, made the same connection. He would deflect credit and move the conversation to something else. This is typical. The people who make the most difference rarely think of themselves as exceptional. They think of themselves as competent, and they expect competence from those around them. But competence, applied with intelligence and courage, becomes excellence. And excellence, multiplied across thousands of individuals in a common cause, becomes victory. The Mustang was excellent because the people who built it and maintained it and flew it demanded excellence from themselves, not perfection. War does not allow time for perfection, but excellence, the best possible outcome given the constraints and the chaos and the fact that lives hung in the balance. That was enough. In fact, it was everything. The sky over Germany is quiet now. The contrails of bombers and fighters have long since dissipated. The cities that were bombed have been rebuilt. The airfields where Mustangs once stood are farms or industrial parks or have disappeared entirely under suburban sprawl. The men who fought that air war are mostly gone, and soon there will be none left. But the machines, a few of them, still fly, and when they do, when a restored P-51 climbs into a clear sky and the Merlin engine sings its particular song, there is a moment when the past becomes present. The people watching, if they know the history, might think of the pilots. They should also think of the mechanics, the men who worked in darkness and cold to keep those planes flying, the men who saw a problem and fixed it, who refused to accept that good enough was sufficient, who made unauthorized changes because they knew those changes would save lives. Their names are mostly lost. Their contributions are mostly forgotten, but their work remains, built into the aluminum and steel, invisible but essential. The Mustang was invincible at altitude not because of a single decision or a brilliant innovation, but because of the accumulated wisdom and effort of people who cared enough to make it so. That lesson, if we are wise enough to learn it, might be the most important thing the Mustang has to teach us. That excellence is not an individual achievement. It is a collective one, and that the unsung, the anonymous, the people working in the background are the ones who make victory possible. They were then. They are now. They always will be. The final image is not of triumph or glory. It is quieter than that. It is a mechanic, his name forgotten, standing in the cold English dawn and watching a Mustang he worked on all night taxi out for a mission. He watches it take off, watches it climb, watches it disappear into the clouds. He does not know if it will come back. He does not know if the modification he made will hold. He only knows that he did everything he could, that he used every bit of skill and knowledge he possessed, that he made the plane as good as he could make it. And then he turns and walks back to the next aircraft, because there is always a next one, always more work to do. That moment, repeated 10,000 times across 100 airfields, is the hidden foundation of victory. Not the battles or the speeches or the medals, just people, doing their jobs with competence and care and an unspoken understanding that what they do matters. The war depended on them. History has mostly forgotten them, but the Mustangs remember. Every time one flies, it carries with it the fingerprints of the mechanics who made it invincible. And for those who know how to listen, that is enough. The engine's roar is their monument. The plane's survival is their reward. And the silence that follows when the mission is done and the aircraft returns safely home is the only thanks they ever needed. The sky remembers what we forget. Somewhere over what was once enemy territory, now just farmland and quiet towns, the contrails have long since faded. The men who flew through that sky are gone. The men who kept them flying, who worked through frozen nights with tools and intuition, are gone too. Their names were never carved in marble. Their decisions were never studied in staff colleges. But every time a restored Mustang climbs into clear air and holds altitude without faltering, they are there, in the smooth hum of an engine that refuses to overheat, in the confidence of a pilot who does not have to choose between power and survival, the mechanic who filed down a radiator scoop by hand, who trusted his eyes over the manual, who made an unauthorized change because he knew it would save lives. He won no medals. He received no commissions. He simply went home when the war ended, carried his toolbox back to ordinary life, and never spoke of what he had done. But his fingerprints remain, pressed into the aluminum, invisible to everyone except those who understand that wars are not won by the famous. They are won by the forgotten. And the Mustang, invincible at altitude, was their monument. Silent, enduring, true.